thank you, Noah, for joining us. Really appreciate, really grateful that you could join us. And I've given everyone like a brief introduction, so I'll just let you. I don't want to waste any more time, so I'll just let you run with it, if you don't mind.
Great. Yeah, no, I'm happy to. And I guess, I'm thinking critically of how to use this time that we have together to you all's best interests. I could wax poetic about lunar exploration. I could go on and on and on and on and on. I think what I want to do, unless I hear anyone says no, is I think I'd just like to dig into the data that LRO has gathered over the last 12
Yeah, that
years.
sounds interesting. Yeah.
Okay.
I did mention to you that we had Ben talk to us
Right.
previously,
Yeah.
so we've got some kind of basic knowledge, I would say.
Mhm.
It'd be great if you could build off that. That would be brilliant.
Sure, yeah. And so Ben Feist is a dear and friend of mine, and so you got everything you'd ever want to know about anything from Ben. So I'm not going to, but I want to talk about the moon. So I work on this incredible mission called the Lunar Reconnaissance Orbiter. We've been at the moon now for 12 years. We were supposed to be there for as much as 2 years. So we have now, gone on 10 years longer, a decade longer than we had ever planned, longer than any mission that's ever been at the moon has done. So we have really been this incredible asset at the moon. Again, launched in 2009. We were initially supposed to be charting out landing sites for human exploration that was going to be happening by now. And that didn't happen. NASA changed priorities, but of course now we're in the era of Artemis, of this sort of new age of human exploration of the moon. And the great thing is that now the moon has gone from this object as it was in the 1960s, this target for a space race, to this incredible scientific asset that we have literally in our backyard, 3 days away. And so what I'm going to share with you is just one tool that we on the LRO team have developed, thanks to our camera team, that basically takes all of the data that we've collected over the last 12 years and makes it available for the world. We've collected over 1.3 petabytes of data, which is the most data of any NASA planetary science mission ever. We benefit from being so close to the moon, so we can get relatively high bandwidth, and we have these incredible, basically high-def instruments that are in orbit around the moon now. So what I'd like to do is sort of walk you through how we use this tool, in particular looking at the South Pole, and maybe spur discussion and ask questions. And I'll try to wrap up about 11:55 local time so that I can help get my daughter fed for school. As much as Spanish lessons are going on, I've also got to make lunch. That's the plus side of working from home for the last 16 months. So let's talk about the moon. I'm going to share my screen, and if all works well, which it should, because I've been using Teams now every day for 16 months, you should see a Safari window with what looks hopefully familiar to everyone, the near side of the moon. Great. So this is a website called QuickMap. You can see the URL at the top, quickmap.lroc.asu.edu. And QuickMap is, think of it as Google Moon, but for scientists and the public. Everything I'll show you is in publicly available form and usable by anyone, but I use it as this incredible resource to be able to work with the data and basically check out what the moon is. Remember, 50 years ago, we had, obviously telescopic images of the near side of the moon that you're seeing here. We had lunar orbiter data of select areas of the moon, all of which were essentially snapshots. But now we have a spacecraft that's been at the moon for 12 years, and we've been imaging it over and over and over again. And because of that, we're able to see changes. We're able to detect new impact craters that have formed during the life of LRO, something we've never been able to do on the moon before. We're able to see the moon change underneath our feet. So we're not just mapping the moon in 3 dimensions, but we're mapping the moon in 4 dimensions. And so just to highlight kind of why I think this is such a useful data set and why I'm such a fan of it, which is, obviously I'm a fan of it. I'm I'm the project scientist for it. It pays the bills, but as a data source and insight into the moon, again, our nearest neighbor in space, I like to think of the moon as the 8th continent of the Earth. it tells us what the moon actually is and provides us the base set of information that we'll use to go back with humans and future missions. So I'm going to switch projections for a moment and lay out the moon now like a menu in front of us all here. And again, I'm going to sort of just zoom out so we can kind of get a perspective. So in the center of this area is the near side of the moon, and then on the other side are the far side is the far side of the moon. Let me just zoom in for a moment at my particular favorite location on the moon. This is the Apollo 17 landing site. And you know what's so remarkable about this data set is not just that we have all this data, but as we zoom in, of course, the high resolution camera actually allows us to see the hardware that was left behind by the Apollo astronauts. And so at the center of the image here, where my cursor is the Apollo 17 landing site. That shadow at the middle is the bottom half of the lunar lander, the lunar module. Of course, the crew took off from the lunar surface and left the bottom half behind. This smudge right here is the rover that they drove around for 3 days while on the surface of the moon. And over to the left are some of the rocks that they investigated, boulders, as well as some hardware that they left behind as a surface science experiment. Now, what's wonderful is that not only do we get this, as I said before, this one image, but if you draw a little square right around the landing site, I wanted to draw a polygon, not a line. Let me start from scratch. This is the hazard of talking on the first day back to work after a long weekend. My mind is not completely firing on all cylinders. But for instance, I can take a look at any number of the 26 images that are available here that have been imaged on that one particular location. And we can filter it by any number of criteria. Resolution from 0.4 meters per pixel, so 48 centimeters per pixel, up to images of over a meter per pixel. And so let's just slide this down to the highest resolution images. And so you can see now that we have a few of these that are that we've acquired over time. And I'll zoom out a little bit just to get some perspective. So we image these areas in these long strips that basically use the spacecraft kind of like a scanner, where the spacecraft is moving on, the camera turns on and then turns off. So we build these long noodles of images that we acquire on every orbit. So we've got, again, many ways that we can cut the data and look at particular areas. Let me just put a spot down. Let me see where I want to go. Oh, here we are. Sorry. See now I'll slow down, and if anybody has questions, please speak up, because I'll just talk and talk and talk.
Sure thing.
So if I drop a point, I can look at every image that was acquired underneath this point. And so what this allows us to do is, again, take this 1 petabyte of data and basically make it available to the world in a relatively easy format. Now what this is doing now is inquiring every image taken underneath that point. And so as you scroll down, you can see image after image, and see each image has the spot of the lunar module in it there somewhere. You can get a change in, you can down select or sort the images based on where the sun is in the sky. And so all of these things become very useful tools for saying, well, I want to look at a particular location under a specific lighting condition. And let me explain why that's important. So I'm going to now change to a view of the South Pole. Why the South Pole? Well, NASA is starting this new human exploration of the moon called Artemis, and we've been told that we're going to go to the South Pole of the moon. Now, why the South Pole of the moon? Well, we now know that there's volatiles at the South Pole. There's water. There's hydroxyls, OH, and so there are resources at the South Pole that we think we might need to use. Now, my doorbell just rang. And so if you'll pardon me for a second,
Sure,
I got to go what that is. I'll let everybody just cogitate on the South Pole.
Okay.
Stand by.
All right. Anybody got any questions?
No, I was appreciating that looks like a void. almost like a hole in the middle. Is it a donut?
Yeah, there's no light on. It's there's a lot of shadow on the South Pole. Permanently shadowed craters. Frozen water.
Okay, I'm back. Sorry about that. Okay, so the South Pole. Let's see. So, we know that this is a really diverse area of the moon, and you'll forgive me because actually, this is probably a better way to actually transition from the near side of the moon to the South Pole, because I often will talk about the moon and then I'll switch from one place to the other and it sort of loses its context. So let me do this in 3D because we can. And basically go from the near side view of the moon, and hopefully everyone's familiar with what the moon looks like, and basically just move ourselves down to the South Pole. Oops, and we'll spin around a little bit. Okay, so here we are. The data is going to fill in here, and so the South Pole is this new terrain for us. All of the Apollo missions landed around the equator of the moon, the central near side portion of the moon. And we want to go to the South Pole because we know there are resources there, again, volatiles, hydrogen. But we also know that the South Pole of the moon is a completely different geologic terrain. It's much older than the other places that we've been. And so it will reveal a completely different history of the moon, a much older history of the moon than the areas that we've been before. The problem is, and if you look at this image, you can already tell, wow, there's a lot of these dark areas. There's a lot of these areas that are in shadow. And so I'm just going to move to a static view of the South Pole for a moment. And I'm going to overlay a map of areas that receive no sunlight, what we call permanently shadowed regions. And so every circle, every area inside one of these polygons never receives direct solar illumination. You can see that there's lots of other dark areas that can be dark for weeks at a time, months at a time, but eventually do get some level of illumination. In fact, what we actually can do is put on a map derived from the topography that we've collected. We have this laser altimeter that has measured the moon more precisely than any other planetary body in the solar system. And from that, I'll just put up the broad scale map of that. And let me give it a color palette here for a moment. I'll try to get one that might be as forgiving for anyone who might have differences in seeing colors. That there are some places in the deep blues and purples that receive very little sunlight. And indeed, there are a few locations, and if I zoom in, you might actually start seeing a couple warmer colors pop up. These areas along here, along these topographic highs. And these are places that get 60, 70, 80% illumination over the course of about 18 and a half years. We haven't found any single location that gets illumination 100% of the time. That doesn't exist. But we do see places that get little small glimpses of the sun for more than 50% of the time, which for most of the lunar surface, certainly all the places that we went with Apollo, we get these areas, get 14 days of sunlight, 14 days of darkness. Well, some of these places get extended periods of time in illumination. And so these areas become really interesting and compelling to us because that's sort of the other resource. There's the stuff that's in the ground, and then there's the sunlight, this power source that is the sun. And so all of a sudden now you have these sort of competing interests of, okay, we want to get material out of the lunar surface, We want to get the oxygen, the hydrogen out of the surface, but we also want to be able to use the sun as a power source. Unfortunately, the moon, well, it's all right there for us to use. And because we have this incredible data set now with LRO, we know where to go. We know that there are these places that exist. We know the surface, the texture of the surface. We can, if I zoom in even more, we can count every crater and every rock that exists there, and you know, find all of those great, you know, some people call them hazards. I call them targets, because as a geologist, I want to go sample all of those boulders. I want to go get all those rocks. The engineers want to avoid them as much as possible, and so it becomes this back and forth challenge. But fortunately, because of this data and its ultimately its ease of use of working with, we can, you know, for now, for any location on the surface of the moon, see what it looks like. You know, in Apollo, we had to do a lot of guessing about what the moon looked like, and now we know. We know what the moon looks like. We know where the boulders and those craters are, and so we can plan our missions around that. What is so wonderful about this tool, this QuickMap tool now, though, is that it allows us to you know, take the data from the domain of the expert, of the technical expert, which is where, for the most part, lunar or planetary data has resided, and really make it available for the entire world to use. So for that one location, for instance, that I clicked on before, you know, here's how many different images came up. You know, there's 337 images at that one location that I clicked on before. Some of those might be you know, there may be complete darkness. That portion of the image may be dark, or it may have been a calibration image. But you know, we've imaged that one random location I picked many times. So we take the data out of the hands of the experts and give them give it to the world to use, which is both wonderful because it becomes accessible and usable by the entire globe. It also means that everyone's looking at the moon and trying to find interesting features. And I can't tell you how many times I'll get an email saying, I think I found some alien artifact. Well, no, you found a rock. That's really great. You found a crater. Cool. So, you know, as much as it's wonderful to put the data into the hands of the public, it also becomes a challenge at sort of mitigating people's expectations of what they see or what they think they see. And so, you know, what we're able to do now is really, you know, again, zoom in and use this data to help plan missions. And you know, I'm just going to put up a layer of the slope of the moon, and particularly for this area that we're interested in. You know, we see slopes, you know, the red colors are slopes of 60, 45 degrees. These are very steep areas, but the blues are relatively flat, 10 degrees, you know, and lower. And so as much as we have all of these challenging environments, it's going to be very cold, very dark. The topography is going to be very rugged. We know that there are little areas in these interesting places that we can land safely and that we absolutely want to explore. And so, you know, this becomes, you know, a GIS, you know, like tool for the world to use. And so, you know, here's a temperature map, for instance, the polar summer minimum temperature. Actually, I'll put polar winter summer maximum temperature, the hottest it ever gets in these locations. And you can see in some places it's 280 Kelvin, but as cold in some places as 50, 60 Kelvin. So it gets very, very cold in some locations and warms up quite a bit in others. But now knowing that the temperature at the surface at any time in the course of a lunar day, how much illumination it's going to get, we now have all of these parameters that we're able to use to help plan our exploration a little bit more intelligently than just guessing, which is essentially what Apollo had to do. They had to guess what the surface would be like. They had to guess how many rocks would be there. They knew how warm the surface would be. And of course, they were only ever there during the day. And, you know, eventually they were able to do Apollo very successfully. But we can build on that and now go off and explore these really challenging but interesting terrains. So I want to pause there. I'm going to stop there and take a breath and open the floor for questions.
Thanks, Noah. Yeah, I was wondering, I guess for future rovers,
Mm-hmm.
are they planning to build like navigation maps using this data?
That's a great question. I mean, ultimately, the image data that we have, again, at its best, is 50 centimeters per pixel, maybe even a little bit better in a few areas. The question I would have is that going to be good enough for any of the rovers if they have to avoid a 10 centimeter or 20 centimeter or 30 centimeter boulder or rock? Certainly the topography, knowing where smooth areas are probably going to be the more important data sets that might be ingested for these rovers. NASA's planning a rover for the South Pole called Viper. And what they're most interested in is again, the temperature, how do you survive? And then using onboard cameras on the lander to help navigate. So I think, ultimately rovers on the surface probably use cameras on board on board their spacecraft. The area that this data becomes most useful for is for landing. We can take the topography, we can take the images, and basically feed that into systems that are collecting either images as a lander gets closer to the surface, or topography, saying this is where we think we should be based on the LRO data, and here's where we are based on what we're seeing, and comparing the two, obviously very rapidly. We call it terrain relative navigation, and basically using what we know about the moon to help guide ourselves there. It's not a GPS system, it's a LPS, a lunar position system, I guess. And so, using all of these different data sets will help us narrow down where we want to go. But I think it's really going to be up to the instruments on board that rover or lander to bring it home from that, that last 1,000 feet to the surface. And then once you're on the ground, now, again, we can say, well, here's a boulder that we can see in our data set. And for that rover that's on the ground, there's that boulder that you see. Being able to tie the two together, but for actually, navigating around, my guess is that any rover will probably want to have its own onboard camera system. And I put in the chat window a link to the QuickMap page.
Thanks, Noah.
Yeah, my pleasure.
Does anybody have any other questions?
And certainly, at any time, often I find that I don't think of the question I want to ask until much later. I just put my email address in the window there. If anyone has anything, oh, wow, I really wanted to ask this, or what about this, or even something unrelated, obviously feel free to drop me a line. I'm always happy to answer your or anyone's questions. But, and again, I wanted to talk about this because this is this particular website, because this is what the mission does. We make data. As scientists, we analyze the data, but the mission makes the data available to the world for free. Every bit, every byte that we collect goes out to NASA's planetary data system for the world to enjoy. And so I look to, anybody who's interested in using the data, and certainly any suggestions of things that we could do better. But I think this is long after our LRO ends, which who knows when that's going to be at this point. We have enough fuel for at least 5 or 7 more years of operations, depending on how much we use. We're in the process of proposing a 3-year extension to keep operating the spacecraft. So I think I leave it to you all to tell us what we can do to make lunar data more engaging. How long does it take to store next images? Oh, okay. So so the camera team, downlinks the data every day. And part of that is precise knowledge of when each image was acquired. And then we can compare when those images are acquired to where we precisely know where the spacecraft was pointing at any point in time. And using systems that the camera team developed, basically can take that knowledge of where the spacecraft was. And we know within half a meter of where LRO is in orbit around the moon at any point in time. And so knowing that and knowing where and when we turn the camera on, we can precisely map that data back to the lunar surface. And so the camera team has their own tools that they've developed. We also use something that the U.S. Geologic Survey has developed called the, and I always get this acronym wrong, imaging software for integrating imaging spectrometers. Unfortunately, the acronym is ISIS, which There's nothing we can really do about that, but we use that to then take that knowledge of where the spacecraft is and where the moon is and combine the two to map that data down onto the surface of the moon. And then that image information is stored. And so the software behind this website is basically, integrates that knowledge of where the data is and puts it into a geographic coordinates, a geographic system that you see here. We do that to the data as it comes down. We didn't have to go back and do it all. They are constantly going back and reprocessing the data to make it better. And let me grab the website of the camera system, since that might help get a little bit more information in terms of how they actually do some of the processing of it. But I can certainly, Duncan, try to get more specifics to your question if that's not quite a satisfactory answer.
I know. You mentioned that that there are resources on the moon that obviously people are interested in using, like helium. Is that a goal of NASA itself to use to sort of mine those resources and use them for human settlement, or or do you want to enable commercial enterprises to set up their own bases?
The answer is sort of both. We want to go with Artemis to the South Pole for extended periods of time. We don't want to just recreate Apollo and do these 3-4 day missions. We want to go and eventually have what we're calling a sustainable presence. And part of that sustainable presence is using the resources that are available there. One of the long-term goals of Artemis is to develop a base camp. Think of it like McMurdo Station in Antarctica, a presence, a continually occupied presence at the South Pole of the moon that uses some resources that are available there, whether it's, again, hydrogen and oxygen and water extracted from the lunar regolith, or helium-3 that's extracted from the lunar regolith. Part of that will rely on commercial enterprise to provide some of that mining operation. Part of it will be material and hardware that NASA brings along as well. And so what's going to be happening at the moon is more, they call it public-private partnership. It's always been the way it was. NASA solicited who's going to build our lunar rover, who's going to build our lunar lander. NASA didn't just do it. But we're going to be looking to commercial entities to be providing some of that support for us at the South Pole. And again, living off the land, using those resources to basically, whether it's make rocket fuel so we can go on to Mars from the moon, or go other places on the moon from the South Pole. I think both are certainly still things that we want to do, but absolutely using what's available around us at the South Pole to make it a sustained presence is going to be something that we're very interested in doing.
Great, thank you.
Sorry, to elaborate a little bit more on that, obviously, this is something that needs to be practiced, right? Is it currently some experiments where such a settlement in the moon is being rehearsed, planned, tried out while still on Earth?
Yeah, so no planned settlement on the moon. I put a link in the chat window to this mission I referred to earlier called Viper, which will be going to the South Pole to sort of demonstrate some of these things. Can we get water out of the regolith? What does the surface actually look like from down below? We can simulate what we think it'll look like, but Viper will be that trailblazing mission. And then we have other smaller missions that we want to send, robotic missions leading up to the first human mission. Certainly on the Earth, we can simulate what we think it'll be like in terms of, okay, this is how cold it will be. This is what astronauts are going to have to do. But until we're actually there and working with the lunar soil, actually, drilling into it, we won't know. And that's the wonderful thing, is that there's lots of unknowns still about the moon. I just spent 30 minutes showing you all the things that we do know about the moon. We still don't know how hard it's going to be to drill into this regolith, how much ice actually is in the regolith. And so part of it will really be this, relying on precursor missions, whether it's Viper or earlier human missions to the South Pole, that help us understand exactly what we're in for these longer duration missions.
a little bit conscious of the time, Noah.
Mhm.
Are you okay for a
You
few
can go
more
on for another
questions?
moment or two. Yeah. And as I said, I've got my email in there,
Sure.
and or on Twitter at NEPetro oh that I put that in quotes at NEPetro. On Twitter is another way to interact with me. And again, you know, we're still trying to figure out where we want to go. We know there's lots of interesting places at the South Pole. There's no shortage of great science that we'll be able to do there. It's just a matter of what the trades are going to be. How long are we willing to be out of Earth contact? You know, the South Pole, parts of the South Pole don't see the Earth all of the time, only see the Earth 50% of the time. Are we willing to be out of communication with these places for periods of time? We're gonna have to figure that out, but we know where they are, and that's great.
Very interesting. Does anyone have any other questions?
Sure. So how often is the moon bombarded by anything?
All the time, continuously. We've imaged probably now in the 12 years that we've been at the moon about 300 new impact craters. But remember, we're imaging the moon postage stamp by postage stamp by postage stamp. There are Earth-based observatories that are always looking at the moon that are able to see flashes, see things hitting the moon. And then at the very, very smallest scale, it's constantly being bombarded by solar wind, by micrometeorites. It's these larger objects that we ultimately end up seeing impact craters for, little holes in the ground, basically. So the largest we've seen so far is 70 meters in diameter, which is pretty small for the moon. But as I always say, if a 70-meter diameter crater formed in your backyard, you'd know. And so, you know, we're able to see the moon change underneath our feet. It's only a matter of time before we see something larger, you know, 100 meters in diameter, 200 meters in, you know, a kilometer in diameter, kilometer in diameter crater, but constantly being changed. But we've only been fortunate to be able to see, again, a couple hundred of these larger craters, which is great because we've never been able to do that before. And so now we can see these perfect, pristine impact craters that are maybe only a few years old, which is essentially fresh, brand new on the moon for the first time ever. And it tells us how the moon is changing. It tells us how planets work.
That must be a little bit scary if you have a base in the moon, right?
Certainly something that we have to consider. You know, one of the most important things that we'll do is to build hardware that operates for decades, or, you know, for many years, has to be resistant and resilient to not just micrometeorites, again, which the International Space Station gets exposed to, but it's these larger things, and not just being hit by an impact itself, but an impact that happens 100 kilometers away or 10 kilometers away is going to eject material out. So you've got to be able to withstand not just the bombardment of things from space, but bombardment of things coming across the lunar surface as well.
I know, it's Will again. If say that somebody wanted to contribute to your work through sort of open source or something like that, would you recommend any particular project?
Well, boy, I might have to think on that, Will. I mean, one project that I'm working on right now is trying to bring all of the data that was collected in the 60s and 70s into a system that we can use to compare to the data that we have now. Now, I just spent some time talking about how we compare old LRO images to new LRO images to see change. And again, there may be 5 years between those two images. Well, imagine now looking at a picture was taken 50 years ago to today and being able to see all the changes that have happened between then. So that's something that we're working on through a crowdsourced project within NASA. You know, I think, you know, crowdsourcing or you know, finding boulders and craters and identifying features is always a long-standing interest of all of us, because there's hundreds and thousands of boulders and craters to identify. You know, I think one thing that certainly is of interest to me is making sure that, you know, again, when we have multiple images, that they're stacked properly on top of each other, and using, you know, not just one image to say, okay, here's what this area looks like, but the 30 images, the 100 images that we have to see, okay, as the sun sweeps across the surface, maybe The sunlight hits the face of a rock at one particular angle and you see this bright pixel. Ah, that's a rock. Finding an easy way to use every piece of information that we have for any one location through the images at least, and using not just one image again, but 10, 20, 30 images at once. How you do that, how you make sure they're aligned properly so that you're not looking at things that are offset from each other, which can become very, very complicated. Matt, I'm going to have to think on that a little bit more, but shoot me an email and help me come up with the right question as well.
Thanks, Will, for that great question. I was just wondering. I mean, we could probably talk all day, and I've certainly got like a load of questions about Artemis, but I think if I asked them, it would just take too long to go through them. Like I was just wondering about the gateway and possibly future, like a future version of the Apollo in real time website, but for the upcoming missions. And I guess maybe if you could summarize that into like 2 minutes, that would be quite interesting.
Yeah, I mean, so the Apollo in real time series that Ben Mphasis has created, tells us how we need to do things in the future. Ben spent all that effort to get Apollo data tidy and lined up as a function of time. We shouldn't have to go back after Artemis and do that. We should do that from the jump, from the get-go, and say, as the mission is coming down, is happening, everything is lined up so that as it's happening, you can go back and, well, what did that astronaut say? What happened here? Go back. And I know Ben is working towards that system for the space station right now. Implementing that for Artemis is going to be really important for us to understand what's happening. So much more data is going to be coming down from Artemis than was happening in Apollo. Whether it's each astronaut with 2 cameras, 1 camera on them, handheld instruments, we're going to want to be able to collate and collect that data in real time so that as a crew member is doing an EVA and starts describing something, we can say, okay, she's describing that boulder. Let's pull up that camera frame and see what it looks like and try to understand the context of what's happening so that we know that when that rock is sampled, we know the full story of it at that point, that we don't have to paste it together from 16 different sources later on. And so that's going to place requirements on, well, the voice transcript and the images have to be time synced to a certain degree. The data that's the astronauts collecting, we need to get that down either in real time or shortly after it's collected and placed into the system automatically. Ben spent so much effort physically time tagging things to make it line up. We don't want to have to spend that effort to time tag and go back and say, oh, wait a minute, this camera is off by 34.5 minutes, so we need to correct it. No, we want to be able to have that done automatically so that as it comes down, it's laid out in not only in real time, but in real place as well, so that we know, okay, that image is taken over by this boulder, this image is taken over by the lander, this image is taken by the place that we took that core sample from, and be able to not put everything just in time, but also in space of where things happen. And so Ben is working towards being able to implement that. The hardest thing now is getting those requirements in now as these systems are being developed and designed so that he doesn't have to go back and agonize over this, after each mission. And that will make all of our jobs that much easier as we try to understand the context for where the samples come from, where the observations are, and merge the two.
Thanks. Very interesting.
Can I elaborate a little bit more? It's a very, very nerdy question. Is relativity plays a part on timing on these videos and communications?
Yeah, I mean, absolutely. And one of the struggles that we have is taking an event that happened on the moon. So on Apollo 11, they had a seismometer, and it was recording these seismic effects of the astronauts walking. But everything is time tagged to Houston time. Well, how accurate are any of those timings? And so there has to be, again, defined initially on the ground, on the surface of the moon, how is everything time tagged? And now for for the things that I'm interested in terms of the geology, 0.5 of a second isn't going to matter. But when you're measuring seismic energy, seismic waves, those things do start to matter. And so, of course, on Apollo, all of the time tagging of data was done on the ground. in Artemis, we'll probably want to have that time tag not only on the ground but also on the surface, so that we can synchronize those clocks as much as possible to Houston time, or UTC more appropriately, and try to avoid any of those discrepancies in timing. Because for seismic and for geophysical measurements, it's going to be much more important than just being a dumb geologist who's interested in the rocks.
Would you expect times to be, in a way, once you synchronize one point, everything to follow, or will you have time to be more elongated on the moon? Or
yeah, there's actually, oh boy, it's been a long time since I've taken any courses in relativity. I mean, certainly they're traveling a lot faster than you and I are here, but when they're sitting on the surface of the moon, I think those relativistic effects might be very, very minor. Certainly that'd be a great experiment. I mean, that's an experiment to make. How much it impacts some of the data that's being collected is probably relatively minor, although not insignificant. Certainly there are going to be ways to whether through lasers from the Earth to the surface, to do those sort of time synchronizations. We do have a spacecraft with LRO regularly, where we shoot lasers from the Earth at the spacecraft. We can see those laser beams when they hit the spacecraft in our laser sensors, and use that to basically correct the clock on the spacecraft. We do add leap seconds and leap time to the spacecraft clock every once in a while, and so those relativistic effects may have to be accounted for. But again, that's well beyond my education as a geologist.
Thank you.